All right, so today we're going to look at graphing square and cubed roots. Of course, there are many other types of roots we could graph, but we're just going to stick with the square root and cube root functions. And so here are some steps we're going to take when we do our graphing individually later. So we're going to start by graphing the parent function values, which we're going to go over in a second, and then plot those in with kind of a dashed graph. So kind of set up what the parent function would look like. Then we're going to multiply all of the y coordinates, so don't change x, just the y coordinates by our a value. Okay, and that's going to do the vertical stretch and compression, or compression, and any reflection over the x-axis all at the same time. After we've done that, if we have an h and k value, meaning we need to shift left or right or up or down, then we'll move our new points to those final locations and graph our final graph. So let's take a look at our parent functions. So here's our first one, the square root. Okay, and the parent is just y equals the square root of x. So we have a table of values to plug in here. And let's start with hopefully some easy ones. So I've pre-picked some values. Let's start by plugging in 0. So if I plug 0 in here, the square root of 0 is 0. So 0, 0 is a point on our graph. If I plug in 1, the square root of 1 is 1. So 1, 1 is also a point on our graph. If I plug in 4, notice that I didn't plug in 2 here because the square root of 2 is not a nice whole number. It's not something I'd like to graph by hand. Same thing with square root of 3, right? But square root of 4, of course, is a nice whole number. The square root of 4 gives us back 2. So write 4 up 2 is our next point. The square root of 5 is not a nice number. 6, 7, 8. The next nice one we'd like to plug in, the square root of 9, is of course 3, right? Square root of 9 is 3. So write 9 up 3. Okay, and then the next one would be 16, 4, right? Somewhere out here, etc. And that would just continue as we go off to the side. So let's try negative 1. Well, if I plug in negative 1, you guys might remember that gives us an imaginary solution, right? In fact, that's the definition of I, which is imaginary. And we don't graph I on the normal Cartesian coordinate plane. So we would say undefined for this point. Technically it's defined, but as an imaginary. And so negative numbers under a square root, undefined. And so we don't graph them on this graph. So in fact, none of the negative numbers, as I go this way for x, give me back a whole or a real answer for this graph. So it actually has kind of a starting point here at 0, 0. And then we get a nice curve that goes through all these points and does continue up and to the right forever. Okay, so if we were writing the domain and range of this graph, so remember domain has to do with my possible x values. And this graph does not go left forever, but it does continue right forever. And there is kind of a minimum value here, which is the x value of 0. So for my domain, I say x has to be greater than or equal to 0. Okay, for the range, which remember has to do with y, that has to do with the up and down movement of my graph. My graph does not go down forever, but it does continue up forever, right? So we go to the right, it does continue up. So it does have a lowest point here, and then would continue up forever. In this case, that lowest point happens to also be 0. So my y values all have to be greater than or equal to 0. Okay, now in more general, where we can do our transformations that have to do with a, h, and k, and remember, of course, h and k, when you're identifying h, it's kind of the opposite of what it appears to be. K, there's no trick with k on the outside, and those controller shifts left, right, up, or down. And the a here, if it's negative, reflects over the x-axis, or if its value is not 1 or negative 1, we might get a stretch or a compression. Okay, now in this case, we don't have like a vertex in particular where h and k are, but we would call this a critical point on our graph. right? It's kind of where my graph starts. So this would be our critical point here. We'll just abbreviate CP, critical point, which was at 0, 0, which is what your h and k values would be in that parent function. Okay, the domain here, anytime you need to find the domain, if you don't have the graph, is you would take whatever this expression inside is, so in this case x minus h, and set it equal to 0, and then solve for x. So here we'd have to add h to the other side, right, plus h. So our domain is that x, whoops, sorry, backtrack. Okay, for the domain, what we always do to find the domain if I don't have the graph is I want to take whatever expression is under the radicand, in this case just x minus h, and remember, in order for this to not be imaginary or be undefined, that it's going to have to stay greater than or equal to 0. Because if it's less than 0, we'd get imaginaries, and those are undefined for this graph, or outside the domain. So to solve this inequality, we'd add h to the other side. We're solving for x here. And we get, in general, the domain is that x is greater than or equal to h. Okay, but that's really just coming from this stipulation that the inside expression has to be greater than or equal to 0. Now for the range, what you would normally do on this graph, if there's no multiplier or something here, we can just use k, but that also depends on if my graph is opening up, like our graph here, or if we get the reflected version. So depending on what type of graph you get, your range could be y is greater than or equal to k, or y is less than or equal to k. Okay, now, if it's not just h and k, if they put some multiplier in front of a, or they do something funky in our graph, we'll look at other ways of finding the range. Okay, next up are our cubed root graphs. Y equals the cube root of x. So again, I've kind of preloaded some values in here that would be nice to take the third root of, which remember saying what times itself 3 times would equal the value we plug in for x. So when I plug in 0, the cubed root of 0 is 0. Once again, we go through the origin. When I plug in 1, the cubed root of 1 is 1. So 1, 1. 0, 0, and 1, 1 show up on a lot of parent functions. Now the next nice number that would be nice to take the cube root of is actually 8. You might remember that 8 is 2 cubed. So what number times itself 3 times is 8? Positive 2. So 8, 2. And the next one we'd run into is actually 27 before we get to 3. So pretty far outside of most graphing windows. But this does, so far, continue in this direction. Okay, continuing up and to the right, very slowly up, but still continuing up forever. However, cubed roots can also have negative numbers under the radical. For instance, negative 1 times itself 3 times is equal to negative 1. So the cubed root of negative 1 is negative 1. Likewise, what times itself 3 times is negative 8? If we plug that in, that's negative 2. So negative 8 is down at negative 2. And we get this graph that actually has like 180 degree, I missed my point a little bit, 180 degree reflective symmetry, or rotational symmetry, I should say, over the origin. But we get a graph that does continue down and to the left forever. So the nice thing is, for my domain and range, the domain is x, how my graph goes left and right. This goes left and right forever. There are no gaps or holes. Our domain is all real numbers. Okay, and for the range, this graph does slowly continue up forever and slowly continue down forever, but it does go forever. So my range is also all real numbers. And the nice thing about this is, even if I flip my graph upside down, it still goes up, down, and left and right forever. If I compress it or stretch it, it still goes up, down, left, and right forever. If I move it left or right or up or down, it will still continue up, down, left, and right forever. So the domain and range, no matter what, for a cube root graph, is all real numbers. Okay, now that's not true for the even roots, like square roots, as we just saw, but that is true for all cube roots. Okay, and the general function here is pretty much the same as square root, but it's just a cube root, of course. So, in this case, we would say this kind of part where it kind of changes directions in the graph, kind of the, I guess you could call this the center, is our critical point this time, but that's where h and k will be located. Okay, so let's try some examples. It says sketch the graph of each radical function, then state the domain and range for each. Okay, so for our first one here, we're given a cube root graph. And if you remember our steps in the beginning, first thing we want to do is make a table and plot our parent function values, which we're actually going to steal, since it's a cube root graph, this table. Okay, so since this is a cube root graph, we're going to start by making a table of cube root values. So -8, -1, 0, 1, and 8. And the answers we got back for these were -2, -1, 0, 1, and 2. So we're going to plot these 5 points, 0, 0, 1, 1, 8, 2, -1, -1, -8, -2. And we're just going to kind of, with the dashed graph, say, all right, this is what the parent function would look like. Obviously, that's not our final graph. Maybe we'll even label it, that's the parent function, the cube root of x. Okay, so next, step 2, multiply the y coordinates by the a value. So we're just going to take all of our y coordinates, and in this case, our a value out front is 2. So we're going to double all of our y coordinates. So just the center column here, we're going to multiply all those values by 2, which gives us -4, -2, 0, 2, and 4. Okay, so we're going to plot these new points, which is -8, -4, -1, -2, 0, 0, 1, 2, and 8, 4. Okay, so now in green, this is my new graph, which has our vertical stretch. But we haven't done any shifting, and in this case, of course, because a was positive, there was no reflection. So this is y equals 2 times the cube root of x. So that's what we've done so far. Lastly, we need to identify h and or k. So I guess we should have said a is 2. Here, this is my h value. Remember, h is the opposite of what it looks like. And because there's no k added or subtracted anywhere, we can say k is 0. So this, my horizontal shift, because it's -1, it means we need to shift everything left 1. Because k is 0, there is no vertical shift. So all I need to do is take my 5 green dots and move them all left 1 unit to find my final graph, which we can do in red. I know it goes on top of the dashed one a little bit here. Hopefully you can tell it is shifted left 1 unit. So there would be my final graph in red, which is 2 times the cube root of x plus 1. So that's what it would look like if I'm trying to pick it out of a lineup. Next, let's do the domain and range. So remember for the domain, for a cubed root graph, the domain and range should be hopefully super easy. They're both all real numbers. It goes left and right forever with no gaps or holes, and it goes up and down forever with no gaps or holes. Okay, let's try number 2. Let's start with a, h, and k. I guess I didn't do that last time. Here, a is 1. H, remember, is the opposite of what it looks like, is +4. And k is +5. So there's no stretch or compression. Since a is exactly 1, it's positive, so there's no reflection. But we are going to need to move 4 units right. I guess that's an R. And 5 units up, since those are both positive directions here. So let's start, though, with our parent function. Remember, we want to pick values that's easy to take the square root of, which are 0, 1, 4, and 9. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So plot those parent function points, 0, 0, 1, 1, 4, 2, and 9, 3. And we do that with a dashed graph, because remember, this is just the parent function. The y equals the square root of x. Next, I would multiply everything by my a value. But since a is 1, it'd be pretty silly to multiply them all by 1. So we can stop there. We don't have to do a stretch or compression or reflection. So we can move on to just shifting left and right. So I need to move all my points 4 units right, which is probably going to take me off the graph for some of them, and 5 units up. So let's start with 0, 0. 4 to the right, 1, 2, 3, 4, and up 5. 1, 2, 3, 4, 5. Okay, so I've done that one. Let's move this to the right, 1, 2, 3, 4, up 1, 2, 3, 4, 5. Essentially, we're just going to be redrawing this graph, but up here now. Move this left, right, 1, 2, 3, 4, and up 1, 2, 3, 4, 5. And if we did that here, obviously we'd be somewhere off the graph. So we can only fit 3 of these in the graphing window. This guy, the last one, ends up going, off the screen there. So there's my graph. Its domain, in this case, remember for square roots, we need to take whatever expression is under the radical, x minus 4, and say that has to stay greater than or equal to 0. Solving for x by adding 4 to the other side tells me for my domain, x has to be greater than or equal to 4, and we can see that. My graph only continues to the right from 4, right? We can also see from the graph, of course, that my graph is going to continue up, but it has a minimum value here at 5. So for my range, y has to be greater than or equal to 5. Another way to find your range if you didn't have a graph is you can plug in 4, its lowest value, into the equation. If you do that, you get 4 minus 4, which is 0. The square root of 0 plus 5, which would give you 0 plus 5, or 5. So it tells you where the y-coordinate of your critical point is. It's at 5, of course. And because my a value is 1, I know my graph is going up, so it is the greater than or equal to 5. Remember, like a negative a value might have been less than, but not this time. Okay, so we're going to do a few more of these. So here's number 3. We've got another cube root, so let's start with those 5 values. Okay, and then plot our parent function points on the graph. Okay, so there's our basic parent function. I guess we should also identify a, h, and k here. So they did try to be a little tricky. Now remember, a is the multiplier on your radical, which is actually the -1 in front here. So a is -1, which does mean we have a reflection. Okay, but since it's 1 exactly, positive or negative, there's no stretch or compression. Now this 3 is actually held to the radical by addition or subtraction. You can actually think of this as being a positive 3 over here. So they just went a little tricky on you. The a value in front is -1, and that 3 is really your k value. That positive 3. H on the inside, remember, is the opposite of what it looks like, so that's +1, which means we need to go right 1 and up 3. But first, we need to multiply, this is step 2, multiply all of our y-coordinates by a, which is -1. So if I multiply all these by -1, I get +2, +1, -1, and -2. And of course, this is equivalent to a reflection over the x-axis here. So plot all these in. Here's our reflection. Okay, so that's y equals negative cube root of x. Lastly, we need to do our shifts. So we're going to move these 5 dots in green, right 1 and up 3. So right 1, up 3, right 1, up 3, 1, 2, 3, right 1, up 1, 2, 3. Oops, I forgot to go right 1 earlier, and I went up too many. 1, 2, 3, there we go. Right 1, up 1, 2, 3. It was this one. See, this is why I usually check them off as I go. I didn't move this. Right 1, up 3, there we go. Right 1, up 3, right 1, up 3. And our last one, right 1, up 1, 2, 3. Sorry, this is a little small for me to see on the screen. So this is our final graph. Okay, and there's my label. So remember, again, for domain and range here, because it's a cube root graph, this is always all real numbers. Okay, one more graph. So we have an a value here. This is a square root graph, an a value of -1/2. So remember, the negative part will give us a reflection, so it'll be kind of upside down. And the 1/2, if it's a value between 0 and 1 for a, then, or the absolute value, it will give us a compression. So we're actually going to see kind of a squished version. h here is -3. Remember, opposite of what it looks like, which means we'll need to be going left 3. And our k value is -2, which means we're going to be shifting down 2. So let's start with the parent function points for square root. And remember, if you forget these for either one, just think of values would be nice to take the square root of. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Okay, so there's our original graph, or the parent function graph dashed in. Next, let's do step 2, which is we need to multiply all of our y coordinates by a. So this would be -1/2 times our y coordinates. Well, anything times 0 is 0. 1 times -1/2 is -1/2. 2 times -1/2 is -1. And 3 times -1/2 is -3/2, or -1.5. Okay, so 0, 0, 0. We've got -1/2, 1, -1/2, 4, -1, that's here, and then 9 and -1.5, 1.5. So you can see not only did that flip my graph upside down, but it's now only half the distance from the x-axis, right? So it's kind of been squished as well. Lastly, we need to do our shifts here, shifting left 3 and down 2. So let's do that. Move everything left 3, 1, 2, 3, down 2. Left 1, 2, 3, down 2. So it started at a half position. We'll just continue that. 1, 2, 3, down 2. And this was just also at a half position. Left 1, 2, 3, down 2. You just kind of hold that half position there. So here's my graph. Starts there, continues down and to the right. And I know it's not a perfect graph, but we'll roll with it there. And I didn't label my green one earlier. Sorry, this was, of course, y equals -1/2 the square root of x. And then, of course, we just finished the full graph. Y equals -1/2 the square root of x plus 3 minus 2. Okay, so for the domain, remember, we can see this on the graph. We can see that x is going to stay greater than or equal to, looks like -3. But we can also get this algebraically by starting with the value under the radical, x plus 3, and saying for square roots, or any even root, really, that has to be greater than or equal to 0. Subtracting 3 to the other side, and we figure out that, yep, sure enough, my x values all need to be greater than or equal to -3. For the range, we can see this on the graph, that it looks like we're only going to continue down from a highest point of -2. So my y values are all going to have to be less than or equal to, meaning below, -2.